Okay, that's enough for housekeeping. I will jump to the theme. The theme is the state planning for ozone. We're going to talk about national ambient air quality standards and other federal use. Our first speaker is Michael Geigert.
Yeah.
I'm a big fan of Michael, and he's a superstar in our HAQAST community. Without further ado, Mike.
Okay, see if the slide advance works. Do I have to? Okay, there it is. Okay, one moment. Michael Geigert, Connecticut Department of Energy and Environmental Protection. I've been involved with HAQAST for quite a while now, since Arlene Fiore invited me to Lamont Observatory years ago. So basically, yep, you go on the next slide. There we go. Basically, I just want to orient you with Connecticut's ozone problem, because we had the worst ozone design values on the East Coast. Now you see the trends there. Basically, to attain the standard, the current standard is the lower line, the lower red line, 70 ppbs. And we have two non-attainment areas, Greater Connecticut and also New York, New Jersey, and Connecticut. And you see at the end, the current design values, the highest in those areas at 82. Our coastal monitor, Greater Connecticut, bumped up to 73. Now, we were pretty close to attaining Greater Connecticut. And as I said here, the increases were due to the wildfire smoke. Everybody from Minnesota over to the Southeast states knows about the Canadian wildfires. Okay, let's move on here. Let's see. And okay, so basically, again, exceptional events. There's a lot of people going to be talking about exceptional events, some for PM perhaps, but for us, it's going to be ozone. And basically, what we have to do is there's 4 events. There's the April events, there's the June 30th, July 1st, and then we have a July 12th and a June 1st and 2nd. We have to get all 4 of these events concurred with from the EPA to attain our goal. On the right, the design value, the top section is for Greater Connecticut. The numbers would be below 71 attainment. Southwest Connecticut will, you know, the trends are such, it's gonna be a long time before we attain the standard, but from 82, the design values go down to 80, and our 4th highs go below 76, which is the key here. So that is our goal for exceptional events. Next. Okay, so basically, I think Amber's probably here in this room, and the Flint Hill fires, you see there, Eastern Kansas, they burn every year, and a couple million acres, plus all those other fires. Look, in Missouri, Oklahoma, Southeast US, agricultural prescribed fires for the most part. Anyway, the plumes are always there. And basically the weather pattern this year was such, it became very hot in April. And the weather pattern for a whole week, all the wind was kind of blowing up the Mississippi River and east. Okay, next. Okay, this is why HAQAST is important to satellite data, right? Because first of all, EPA has a fire smoke map, which is, it tries to update with fire locations and HMS smoke. But we have to, for exceptional events, have to do back trajectories. So here's an example of April 13th, we had our first exceedance. We hardly have exceedances in April. I mean, it's been a long time, and especially of the magnitude that we were seeing. And basically, so if you take 3 days back, on April 10th, this is the fire map for April 10th. Look at the number of fires, satellite detections. You know, a lot of them are probably small fires, but you can see the intensity over Eastern Kansas, right? And even Iowa, quite a bit. And if you go to the right, that is for the April 14th. And again, a lot of fires for 3 days. April 14th actually had higher numbers for us. So there was not a thick haze, but there was definitely smoke. Our PM values were not through the roof. They were, you know, high, good, low, moderate, but definitely ozone enhanced. Okay, next. So this is what we need from the satellites. Obviously, we look at the visible. On the left is our Cornwall monitor. Look at those numbers. Our Cornwall is our rural monitor at 1,500 feet. It doesn't pick up any sources from Connecticut for sure, and usually not New York City with a westerly wind, but you can see the back trajectories on the 14th. This is back trajectories going back to the day before. See the fire there in Northeast PA? There was also a few thousand acres burning in Pennsylvania. And you can see the smoke was heading our way. Look at those numbers. We already had above 70 at 2 of our monitors. The oranges are Danbury, which was south of that Cornwall, which shows the trajectories. But you can see the bump. It's plain that there was ozone enhancement of 30 ppbs just from that smoke plume. So this is what we're dealing with. Okay, next. And I just want to show, oh, good animation. Okay, so we look at AOD. AOD is obviously dependent on the algorithm used. I like to use VIIRS especially, but this is actually the GOES, because GOES is hourly. And you can just see, I mean, you can see the aerosols that the satellite detected. Also a fire in northern New Jersey. So for this event, you know, definitely to us, exceptional. This is going to be the toughest one because besides these fires that are thousands of fires perhaps in Kansas, over the southeast states. I mean, this is, no one's done a prescribed fire exceptional event burn request in a long time. Ours might be the first. Okay, next. So any way you can help us, guys. There it is. Okay, so you look at tropomi. Okay, NO2 doesn't usually last long with the wildfire smoke, but you can see how much it puts out. I mean, as much as an urban area, right? So on that day, on the 8th, this was a week before, a good week before. I mean, they were burning a long time. Okay, and then we go to the 13th, and you can see where I circled, you can see the NO2 off those fires too. So it was definitely, everything from the satellite data is pointing to an exceptional event. And of course, I give a nod to Dan Goldberg's work, because that's what I have up here. Again, a good HAQAST colleague. Okay, next. Okay, and this is again our colleagues, Arlene Fiore and her entourage of students over the years, and Tracey all started, I guess, with these students, from my understand. And anyway, what we'd like to look at is the ratio of formaldehyde or the VOC over NO2, because we'd like to see the trends, how it's doing. Well, New York City tropomi always has that big bubble of NO2, right? But there's also a lot of isoprenes around. Okay, so what they did here, this was the study. Was this a Jin study? This was Tama. I did, okay. And basically what happened here is that if you see non-exceedance days on the left and exceedance days on the top, okay, so that's formaldehyde. Exceedance days are generally warmer, so you get more formaldehyde from the isoprenes, for instance. So, but if you look at the bottom, the NO2 is higher on the exceedance days. And if you look at the ratio of non-exceedance days, you get the blue, which means it's more VOC limited on non-exceedance days because it's cooler. On the right, it's the transition, it's more in the transition stage. So this is the type of work that the HAQAST crew, researchers have been doing to help us out. Okay, next. And this is the trend chart. There's been some work done with the cities, concentrating on getting the ratio, transitional NOx limited ratios for specific cities, and New York City was one of them. But you could just see the trend. Okay, it's NOx saturated over New York City, but the trends are towards transitional. If you look on the right there, you can see over the years, 2005 to 2021, we're getting there. We're getting more to NOx limited. Why do we want that? Because basically, if you look at New York City, they hardly have an ozone exceedance center city. It's NOx titrated. It's the bubble's been collapsing. 2 minutes. Okay, next. And then if we look here, Pandora data. We have a couple of them. Madison is east of New Haven. That's far enough away from New York. But if you look at the ozone days that are 60 ppbs or above, you see the yellow. We're still, a number of them are NOx limited. So even that far away from New York City, it's not quite all NOx limited. But again, this is Pandora. So another valuable tool. Next. And I could not go on without Laura Judd's work. It has stacks. This is preliminary data. I just grabbed this just to show how valuable it is, because this is 250 meter resolution for the slant column. there'll be more refinement to this, but this is just preliminary data, just to show the south winds, and this day it was blowing the plume north of New York City. Hardly anything over Connecticut or Long Island. Next, 1 minute ad. Of course, who could go on without Daniel Tong's work? This is, by the way, these images are in our SIP. The reason I mention this, these are all taken out of our SIP. So this is how valuable this has been. Not your latest one, of course, but this is one of our figures. When you see a figure here, Daniel, thank you very much. This is your, in our SIP, just to show where the emissions are. New York City, bullseye. Next, this should be about it. They're about to pull me off. And of course, we have Temple of First Light, and you saw this. I'm comparing the two. They're very comparable. On the right, I did the GIS. I poured this ArcGIS Pro. We're trying to get the tropospheric ozone column. This is not current. This is proxy data. This is the potential for what we're going to see next. That should be about it. And thank you, HAQAST, for all your support, because we put these into our SIP, and that's what you guys like to see. Okay.
Thank you, Michael, for getting your field to take up the data. We are very grateful for people like you to make utilize our data and make a real impact in the world. Next, I'm going to introduce Pat Reddy. Pat is an independent scientist, formerly with the Colorado Department of Public Health and Environment. Welcome, Pat.
Thank you.
Fiore.
So, I worked at the state of the Air Pollution Control Division from 1990 to 2015. I was the lead forecast and research meteorologist there. And I used a lot of satellite data in the 90s, mainly just visible satellite image products. After 2002, I started to use MODIS satellite image products, and sometime around 2010, I got really interested in stratospheric intrusions of ozone, which are pretty common along the Front Range. And shortly after that, I met a lot of people in HAQAST, the predecessor to HAQAST, and got really interested in using trace gas measurements from satellites for SIPs, exceptional event analyses, and forecasting.
I guess
How does this work? Oh, yeah, so Colorado has a robust program of oil and gas emissions control regs that really ramped up around 2014 and continue to be improved. Many of these were incorporated into the state implementation plans for ozone. And during that time, oil and gas production in the Wattenberg field, which is in the non-attainment area, increased around 300%. And so the question I'm addressing here is, how have oil and gas air quality impacts changed during this period?
I can switch it from here if that's.
She'll move it for you.
Thank you. So this is the study area, and this was a study area for two papers that is published in the last year. On the left, the non-attainment area for ozone in the Denver Metro Northern Front Range region is outlined in blue. And the AIRS level 3 product, methane grid cell centered over the metro area and the oil and gas field is outlined in red. I plotted the key ozone monitoring sites with little red dots and labels. Platteville has a state trace gas measuring site, and they measure ethane there. I used ethane as a tracer for oil and gas VOCs. And I subtracted methane from Niawat Ridge, which is off to the left of the grid cell, to calculate methane enhancement from the AIRS product. And I'll explain why I think that's possible. On the right, I've plotted high split monitor footprints for Fort Collins West and Chatfield. Fort Collins West at the top is highly sensitive to oil and gas emissions, the ozone concentrations. And Chatfield is the least sensitive to oil and gas emissions. So there's a gradient from north to south there. I defined a OMI NO2 grid space over the oil and gas area. At the top in green, and at the bottom is an urban OMI NO2 grid cell. And so I was looking at how did fourth max ozone change during about a 10-year period, and were those changes related to reductions in oil and gas emissions? Could you mention? So, why do I think I could use AIR's methane for this? The AIR's instrument is not very sensitive. It's looking at a weak infrared signal. It doesn't give you a true concentration for any level. It kind of aggregates concentrations over a deep vertical layer or products at different levels in the atmosphere. And generally, it's only sensitive to methane above 2 kilometers and very sensitive to methane in upper troposphere and stratosphere. I noticed that in Colorado, the AIR's methane product for 700 millibars is highly correlated to planetary boundary layer heights. And you can see that in this plot. The labeled contours are the methane product, and the solid contours are planetary boundary layer heights. And the bullseye is where I live. It's a high altitude desert, 7,000 to 8,000 feet. All the solar radiation there gets turned into sensible heat and pushes the boundary layer way up. There are no sources, no significant sources of methane from the surface there. In eastern Colorado, there is a lot of methane along the Colorado border at the edge of the plot, but AIRS doesn't see it because the PBL heights are not high enough compared to the central part of the state to push enough methane into the view of the satellite. To do kind of a reality check, I compared the AIRS 700 millibar product with the NASA P3 spiral flights from 2014 over the non-attainment area, and they were within about 15 ppb. And I won't get into it too much, but we've determined that we and others have determined that the ethane at the Platteville site is representative of the oil and gas emissions in the oil and gas field. Next slide. So here are some results. So the upper left in blue is the methane enhancement that I calculated, plotted along with the ethane. They track well, even on a year-to-year basis. In the lower left slide, those are the year-to-year differences. So when ethane goes up or down, the methane enhancement follows suit. As a test of this method, I also applied it to the Uinta Basin, and I got methane enhancements from John Lynn at the University of Utah and plotted those against the AIRS-based enhancement that I calculated. Those also track pretty well. Next slide. So here on the left side, I've compared fourth max ozone for 2 of the sites that are most influenced by oil and gas emissions. Those are the lines, and I removed all the potential exceptional events so the signal would be stronger. And the top one on the left has fourth max ozone versus ethane at Platteville, and the bottom one has fourth max ethane versus the methane enhancement. And then in the upper right, I plotted one of the more recent SIP oil and gas VOC emissions inventory numbers and the Platteville median ethane versus the basin methane enhancement derived from the AIRS data. And you can see the fits are really good. Even the inventory has an R-squared of about 0.8. Ethane has an R-squared of about 0.2. And they intersect the enhancement line at around 12, which is 30% of the 2012 starting point, and that's similar to the 25% of local methane that Gabby Patrone determined to be from non-oil and gas sources. So that's kind of a check on the method as well. Next slide. So I won't get into why I think this was a legitimate thing to do, but I did partial regression plots of Fort Collins West ozone versus ethane as a tracer for VOCs, and then versus OMI NO2 as a tracer for NOx. And Fort Collins West fourth max ozone has a correlation coefficient of 0.99 with ethane. And the base factor, if you know what that is 483. That means it's 483 times more likely than the null hypothesis. And the base factor for the OMI NO2 analysis is much lower. And there's a 28 times greater probability that the ozone change was related to VOCs than to NOx, based on this kind of analysis. Next slide. So this is sort of a summary plot. I've got monitor footprints in the color contours. And you can see that Fort Collins West on high concentration days is getting air from the oil and gas fields. Chatfield is getting air from the Denver metro area. I've plotted in color coding the size of the base factor for the correlation between the ozone data and ethane, and highest and considered decisive at Fort Collins West. It's lowest and considered not really meaningful for Chatfield. And you can see the oil and gas wells plotted there as well. Next slide. So in conclusion, correlations between the air's methane enhancement, Fort Collins West and Rocky Flats fourth max ozone, the SIP, VOC inventory, and ethane range from 0.88 to 0.96 with really high, strong to decisive base factors. Paper that Courtney Taylor from Ramble and I did a year ago, we showed a 70% reduction in ethane at Platteville and an estimated 50% reduction in methane in the basin in that grid cell. Zhao Liu, Daniel Jacob, and others just published a paper where they show 11% decrease in methane based on a inversion of surface measurements and GOSAT data in that oil and gas basin. And their supporting information file shows a 60% decline in methane from 2012 to 2019. So that's pretty close to what I got in the other study. So it's possible that oil and gas VOC contributions to the annual fourth max have decreased by about 2/3 at those two sites that are most sensitive. And this could be really useful for assessing the progress in reducing ozone as a part of the SIP. Next slide. So this is just a quick summary of what I think past, present, and potential future uses of satellite data for air quality management in Colorado would be or are, including forecasting ozone, PM2.5, visibility, blowing dust, health messaging, wildfires. A lot of exceptional event analyses in the state have used or did use satellite data. Last year, I had a short-term appointment with the Air Pollution Control Division, and I did a smoke ozone exceptional event analysis. It was about 160 pages, took 9 months. But there's more of that to come, obviously. The state does a lot of work on air quality related environmental justice. I'm not sure if they're using, anyone there is using satellite products right now, but I'm sure there's an opportunity there. And the meteorologists in the division are really excited about being early adapters for tempo. And I think could be interested in looking at the air toxic issues related with oil and gas emissions in that area. There's a new state law that requires the state to track air toxic impacts. And that may fit into Ted Russell's hydrogen project. Thank you.
No, good.
Thank you, Pat. So next I'm going to introduce one of our finest data member, Arlene Fiore, and he is a professor at MIT. And
So yeah, maybe I'll just start and say that I'm really excited to be part of this panel, and in particular, I guess my talk ties more closely maybe than I realized with Michael Geigert. So he kind of set me up really nicely. Thank you. And I want to acknowledge Dankui Tao Ma, who is a graduate student who's leading the analysis that I'll be showing you today. And it's not working. It's just, okay. Sorry, I have a lot of this. If you want to go ahead. So we're focused on just go back for 1 second. Oh, sorry. The June to August time period of summer 2018, when the Long Island Sound tropospheric ozone study was taking place, which provides a nice opportunity to connect what Tropomi sees from space with what's going on in the ground. And so the question that we're mostly going to focus on today is, how does the ozone form and chemistry vary along urban to rural gradients and with time of day? And then go ahead, thanks. So I did, since we're in this, it's sitting in Utah, where background ozone is often a concern. I did want to just use this slide that Terry Keating from US EPA put together based on some earlier modeling work we had done in my group. And what you're looking at is just a breakdown according to one model of the different contributions of different sources to total ozone. And of course, what's measured is only total ozone, but the way that the National Ambient Air Quality Standards are implemented, we need to understand what the breakdown is among these different sources, or the source attribution for each exceedance day. And this just highlights the difference as an example of what's going on, for instance, in New York, New Jersey versus the Intermountain West. And in the past, I've had the opportunity to work on kind of all of these different components. And so I'm happy to talk more about that in the discussion. But for today, Lizzie, we're going to focus, like I said, on the local ozone production in the New York and Connecticut area. Please. Okay, so I think I don't need to spend so much time on this plot because Michael showed a version of this, but earlier work by Tao Ma had used this formaldehyde to NO2 ratio as an indicator, building on decades of work previously, for whether the ozone formation locally is more sensitive to emissions of NOx, in which case you're in the browns on this color scheme, or if you're NOx saturated or VOC limited, which means that as you reduce NOx, you expect a disbenefit to ozone until you reduce NOx enough that you get into that NOx sensitive regime. So we're excited because with all of these in situ measurements from the summer of 2018, and actually also this past summer, but so far we're still focused a few years ago in 2018, we have the opportunity to really explore what's going on the ground in the chemistry on individual days at individual sites, and how much local variation there is, which could be really relevant for how we interpret our upcoming tempo data. And so what Tao Ma has done is, for each of these sites that are shown here, she's simply running a box model constrained with observations where possible, and where not possible, she's using species concentrations from the WRF CMAX simulation that NESCOM, the Northeast States for Coordinated Area Use Management, had run, specifically Alex Caramellis, at 1.33 by 1.33 kilometers squared resolution. And so just to show you, this is what ozone looks like. We're just showing you 2 example days at these 2 example sites. Queens College is in the urban core of the New York City, and Westport is downwind along the shoreline of Connecticut, one of the sites where high ozone is often registered. She's contrasting a high day in solid and a mid to low ozone day, same day of week, I believe, in the dashed line. Okay. And so actually, it's not the same day of week in this particular example, but we see higher ozone because that's by definition how she selected her breakdown across the days here. So in the next plot, what I'm showing you is the local ozone production. calculated with this box model constrained by observations. And what we see, perhaps not surprisingly, but it does get to this question of how much is transported, how much is local. We see higher ozone production at both sites locally on the higher ozone days. And she's digging into these now. I think there might be something that pops up. Okay, so she's digging into those also to try to do sensitivity simulations with a model to NOx versus VOC. But this begs the question of what is the local chemistry at these sites and how does it differ across sites and on individual days? And so I think some of you are very familiar with these plots, but there may be people in the room who aren't. These are ozone isoplots that are showing, thank you, the nonlinear dependence of ozone production in the contours on the left, if you focus first there, as a function of NOx on the y-axis, and basically a marker for how much VOC there is contributing to the chemistry on the x-axis. And you see that you have these two regimes where if you reduce NOx in the bottom right, the orange arrow, you're NOx limited, you're going to reduce ozone. If you're in the upper blue arrow situation, as you reduce NOx, you can actually increase ozone. And in that regime, you might be more effective with reducing your local VOC, although if it's from isoprene, that's going to be very challenging to do. I just wanted to highlight that earlier work by Xiaomeng Jin, who's a professor now at Rutgers, tried to construct an ozone isoplot from the long-term measurements we have from the OMI satellite going back. So she's aggregating across years all the urban sites in the AQS network across the country, sampling them at overpass time, and looking at what the probability of a high ozone day, which was defined as exceedance of 70 ppb, if I remember correctly, as a function of the satellite tropospheric column NO2 on the y-axis and the formaldehyde column on the x-axis. So what Tao Ma is doing, if you can flip, thank you, is at the Westport site, we actually had the in situ formaldehyde measurement and NO2 measurement to look at this space at a single site. Also, this is all hours, so we're looking over the course of the day and across days. But you see the same kind of nonlinearity occurring where you're color-coded now by ozone concentration. And interestingly, I'll just call your attention that it looks like ozone correlates really strongly with formaldehyde in the bottom part of the curve. And I think, can you advance? Thank you. But before I go to the formaldehyde ozone, we wanted to take a look, since we have the Pandoras, which are measuring vertical column tropospheric NO2 during this field campaign at both of these sites, and we have the in situ monitor. We can look at the surface NO2, which is the color that you're looking at throughout the time of the day. Of course, we have that for 24 hours. We just have the Pandora in black during daylight hours. But what I wanted to highlight here is there is a delay in the morning peak in the column relative to the surface. Others in this room are doing similar comparisons and have pointed this out before as well. But that's missed by that once a day 1:30 overpass. And of course, we're excited to have tempo kind of hopefully giving us something similar to the Pandoras. One more pop up. I did want to highlight Jeff Getty's work. He's a professor at Boston University who has pointed out the role of sea breeze at many of these sites, including his focus is in the Boston area, but that certainly applies to the Westport site as well. And that the fact that the sea breeze is playing a role in the local NO2 surface to column distribution can matter for our retrievals. So something that we want to be thinking about. Next slide. Okay, so coming back to this formaldehyde to ozone correlation, we're building on our earlier work from Jason Schroeder and Katie Travis that showed that column formaldehyde using airborne data, thanks to Laura Judd and Scott Jans, I guess Scott Jans for the formaldehyde, and ground level ozone, as well as ozone and related oxidants, really meaning ozone plus NO2. And so you see a strong correlation here, and again in the in situ data. And she's looking at how this correlation varies with time of day. And that's what you're seeing in the solid line here. It seems to hold up as a high correlation for ozone versus ozone plus NO2 throughout much of the daylight hours, but strongest, interestingly, in the morning. And so we're interested to dig into this further. Advanced, thanks. Okay, quickly, I just wanted to highlight two more things. We have some work going on looking at air pollution, meaning ozone, PM, and heat, and how often they co-occur and how that varies from year to year in different regions of the country. And there's questions that I think plots like this beg, which are at the bottom here. And so if anyone's interested in that, I'd love to talk to you. We have some, yeah, go ahead, thanks. new modeling spinning up that Toma is doing with this global musical grid that allows you to nest down over a region. In this case, the standard configuration is over the US. And Toma spent a lot of time this summer getting hourly NEI 2017 emissions in for her 2018 simulations. So this is a place where we could use this tool for background and local chemistry, that we're excited about that. And then in my last probably 30 seconds, I wanted to highlight the HAQAST new Tiger team that just kicked off, that's focused on air quality and health applications for surface ozone from Tempo. And of course, we're coordinating with our Reddy and the early adopter program. We had a series of listening sessions this summer with about a dozen, including many of you in the room. Thank you for that. And so the slides will be online, but we have 5 themes that emerged that we're going to focus on with a coordinator for each of these. Everyone is welcome to join our calls. The next one is November 13th at noon. Final slide. But we have 3 types of deliverables that we're probably going to be focusing on in this team. But please come talk to us if you're interested. We're spinning up, and it's a great time to get your input. Thank you.
Exactly 10 minutes. Okay.
Wow, good.
So,
I'm shocked, Dr.
Our last speaker is our awesome lead for HAQAST, Tracey Holloway. She's a professor of the University of Madison.
Great. Well, it's really a pleasure to be here. It's been a great meeting, and I'm especially thrilled to be on this panel because, you know, one of the kind of over coffee conversations we've been having for the past couple of days is I believe that Pat Reddy and Michael Geigert were the first 2 air quality managers in the world to use satellite data.
No. Here.
Here. So it's exciting to be here with them. And of course, a lot of our work has been in collaboration for many years with Arlene's group. So what I'm hoping that by the end of today's talk, you are excited about using these ratios of formaldehyde to nitrogen. And here's just an example from the NASA Earth Observatory about how satellite data, as you've heard already, can help identify whether ozone controls on NOx would be more effective or ozone controls on VOCs. And this line of analysis is something that's been evolving really over 20 years. And of course, this is not a comprehensive literature review, but just a narrative of how some of the information has moved forward, especially relative to HAQAST and my own personal experience. So Sandy Silman, who's retired, is one of the leads on thinking about these VOC to NOx ratios. Coincidentally, we went to the same high school in Illinois. Little factoid. Then Randall Martin, who's now, of course, a HAQAST member at WashU, he wrote a paper in 2004 that Arlene was a co-author on, using space-based data to diagnose ozone sensitivity. And so this idea has really gone back almost 20 years. And then in 2010, Brian Duncan used the OMI data. And in that analysis, he came up with some early thresholds of at what ratio do we consider it VOC limited and at what ratio do we consider it NOx limited. And so then actually it was at an HAQAST meeting back in 2012 when I met Pat Reddy, and I asked as just a small talk, have you ever used satellite data? And he said, yes, I've used Brian Duncan's OMI ratios in a presentation to the Pollution Control Board in the Front Range to think about whether NOx or VOC controls are more useful. And I thought, wow, that's amazing that this has been already used in a very applied policy framework. So actually, I worked with Pat and the outreach manager at the time for HAQAST, Sarah Whitman, to write a profile of his work in 2014 on integrating satellite data into the air quality management, the experience from Colorado, which was part of a 2014 special issue. And I was so excited at the policy relevance of this indicator ratio that when a student of mine, Xiaomin Jin at the University of Wisconsin, was thinking about what would be a good thesis project, I said, well, why don't we use these indicator ratios over China? And so she wrote that paper in 2015. Loved it, loved the global chemistry angle. And I said, well, if you're interested in global chemistry, maybe you should go do your PhD with Arlene Fiore, which she did. And so then she continued that work in 2017, moving it forward. And as Arlene mentioned, Xiaoming is now a professor at Rutgers University, continuing that work. Next slide, please. And so then in 2020, Xiaoming started rethinking this question of what are those thresholds where it goes from NAAQS to VOC limited. And now Xiaoming's work from 2020 is really the state of the art on what thresholds should be used to determine where ratios indicate NAAQS limited and where they're VOC limited. So I was so excited actually at the 2021 HAQAST meeting to see that Arlene presented some of Talma's work, and Talma was also an undergrad with me at Wisconsin, which is exciting. And so Talma had done work actually seeing that it's not just the average ratio of formaldehyde to NOx, but it differs on high ozone days versus lower ozone days, as Arlene has mentioned. But you know, my feeling was that this is such an exciting result. And I've been excited about this topic for 10 years, but there's always this question of how can air quality managers calculate these formaldehyde to nitrogen ratios? Because it's actually trickier than it sounds to do this and average over the days or the time periods that you really want to work on. And so I had another undergrad and postgrad intern, Jennifer McGinnis, who's here in the room. Hi, Jennifer. And who's now a graduate student at Colorado State University. And I asked Jennifer if she could go through and try to look at every single platform that could possibly be used to calculate formaldehyde nitrogen ratio and think about how they could be user-friendly to the air quality management community. So she wrote an analysis. I'll present it here. It's been accepted for publication in the special issue on ozone coming out in December for EM. So it's you can see it there, but here's a preview. And so looking at some of the main data distribution platforms listed in the column on the left, and thinking about them in terms of ease of use. Do they allow temporal averaging? Do they allow you to divide variables, which you need to do for these ratios? And do they include tropomi, which is because Tempo is not yet releasing data publicly, tropomi is the best data to be using for this over the United States or most places in the world. And if you look at that list, the places that are easy to use don't necessarily allow the kind of calculations that is necessary. And as you move down the list, you can download the data into Python, which allows you to do everything, but it's a little tricky. But in the middle, you have that Google Earth Engine. And to our knowledge, nobody had been using Google Earth Engine in the peer-reviewed literature or we've seen online to analyze tropomi, even though all the data are there. So next slide, please. Jennifer, started playing around with it and really concluded that Google Earth Engine is the most user-friendly approach to be calculating these formaldehyde nitrogen ratios, because it allows you to average over your days that you are selecting and calculate the product or ratio of variables. And this is just a screenshot of what that kind of interface looks like. It's not as point and click as NASA Worldview, but it is. You don't have to download any of the data and you don't have to know Python or anything like that. Next slide. So one of the things we wanted to do was to see if we could replicate the analysis from Talma's paper over New York City. And we considered the high ozone days and low ozone days and total days. And we wanted to sort of, again, make it as painless as possible. So the way we parsed high days and low days was simply using the tile plots that are available from the EPA website, and we called the green and yellow low, and we called orange and higher high, and then used these pre-made plots from EPA to be the lens that we used to diagnose these different data sets. And we found the same result, of course, the same quantitatively for New York, even though it was for a different year. This is 2022. We also did it for Denver, just to look at a very different city, and found a similar result, that it was more VOC limited on, more NOx limited on the higher days. Next slide. So then when I work with a lot of undergraduates, and one of the things I love about working with undergraduates is that then they can learn something new quickly, and it helps me see, is this quick to learn? So we have a new student named Ragad Bajuda, and she used some tutorials that Jennifer had written to use Google Earth Engine. And then she did the same analysis, but now for every year that Tropomi data are available, and she did it for 100 cities in the US. And this is looking at New York, and again, the same result, that the higher ozone days are more NOx limited. Next slide. But then we looked at some other data like Houston, and here it isn't consistent across years. Some years, the high ozone days are more NOx limited. Other years, the high ozone days are more VOC limited. Next slide. And in Las Vegas, actually, we found that across all years, it appears that the high ozone days are more VOC limited. And so I'm not here to make some sweeping insight as to how cities differ, but more to say that you can figure it out for your own city and your own region. Next slide. Using Jennifer's excellent tutorials. And here she did it over the state of Wisconsin. And so we put these tutorials at our website, hollowaygroup.org/tutorials. And we'll also be linking them from the NASA HAQAST resource page. Next slide. But this also has led us to think about the question of, is there a way to make this last flexible category, moving it from being difficult to maybe being like medium? It's, again, never going to be point and click, but how can we make it easier? Next slide. And I'm going to bring back to my new favorite paper that is the UK from authors Potts, Van de Hey, and Reddy, because they surveyed scientists and researchers and stakeholders and data users to ask, would you rather download pre-processed uniform data sets, or would you rather have the raw original data because you have the in-house expertise? And this is a big, big difference between the research community and the user community, where the researchers want the raw data because they have the capability to download and process it, and most user organizations would rather have pre-processed outputs that are easier to use in like GIS or Excel. But if we can get the expertise from the left side and make it more available to the right side, maybe it's one more way of bringing these communities together. Next slide. So this is where I am going to advertise our second set of tutorials, which were developed by my PhD student, Alicia Hoffman, and my recently graduated PhD student, Gesayanji, because we had used data from the NCAR command language for many, many years. And one of the things I always liked about the NCAR command language is that they had well-organized tutorials, and it did not assume any programming background. And as we migrated to Python, because I work with undergraduates from about 15 different majors, they have not all taken computer science. I wanted to have a way to on-ramp quickly and get up to speed. And so Alicia and Gassan wrote these 8 tutorials. And just yesterday, our IT person sent us how many downloads had they been and who downloaded them. And if you could switch to the next slide, this is actually a map of all the 200 people who have downloaded. So it's amazing. Like we've never promoted them. I guess Google works pretty well because it has led people to our website. But the fact, it was neat to see that a lot of air quality organizations in the US had already been downloading and using our tutorials, as well as academic companies and government organizations around the world. Next slide. So, I've been promoting the HAQAST website, which of course I love, but we've actually used a similar philosophy to support other work in my group, which is the hollowaygroup.org. And if you go under, our work, it links to the tutorials as well. So with that, we'll open up for questions. Thank you.
Thank all the speakers. We have about 7 minutes left for question and answer.
This is the short
I
session.
will respectfully request you to have short questions and short answers, and also we will be voicing
People.
Yeah, the floor is open. Yeah, go ahead.
I just wanted to compliment Tracey for the wonderful tutorial and your efforts to make the, some of the models and software available. And I just want to compliment.
Thank you. Thank you.
I'm one of those.
You're a dot.
You're a dot, yeah.
other questions? That's all. Yeah, that question for Pat. So am I understanding some of your results correctly to show, where you show that despite oil and gas production going up in Colorado, the VOC emissions are going down?
Yeah, and that's controversial. Not everybody agrees that has happened, but the inventory reflects that. Ethane, which is monitored in Platteville, right in the center of the oil and gas field, has been declining, and then there's methane has been declining.
And what's that attributable to?
Well, it's probably a combination of emissions controls and then industry adjusting on their own, in some cases to reduce methane, but probably more likely centralizing facilities, horizontal drilling, all those things that benefit them have also probably contributed to that decrease.
For Michael, I guess in your use of satellite data to sit, how was EPA's kind of response to that? And would that be something you think would be used in boundary designations before you get to a sit point? So say we've got a shared MSA with North Carolina, and could we kind of get ourselves out of the boundary designation using satellite data?
The boundary designation for the,
So an
Yeah.
annotated area.
Yeah. Oh.
I'm from South Carolina, and we're
Yeah.
split in MSA in Charlotte and North Carolina. And looking at satellite data to say, oh, is this coming from South Carolina or is it more of a North Carolina problem? Can we draw a boundary using that satellite data?
well, it has had a lot to do with, you know, the wind trajectories and everything. I mean, obviously, and the with us, I mean, we've been so tied to New York City, it's just there's no way we're ever going to get away from it. I mean, if you have that situation, then you're probably out of luck. But the satellite data, I mean, the Tropomi NO2 we use a lot on ozone events. I mean, we could see, I can plot the HER winds with it, and the flow of the ozone is pretty obvious that where it's coming from. So those are just the tools we use. So the SIPs are really hard for us because we can never prove attainment in any time span. Even though the EPA modeling suggests it, never happens. So.
I've seen the presentation with Air's methane a few times and I've talked to you about it in the past. I guess I do see how at a high altitude, deep boundary layer, Air's could see. But what does it say about methane in other regions? Because you're probably just looking at some variation in altitude of methane, which has a surface source. Have you looked at Tropomi methane to see if you can actually see any signals of point sources?
No, I fit into that right user circle where we like to have things handed to us. So I haven't used much Tropomi methane data. I did find not your tools, but I did discover somehow that you can use Google Earth Engine to plot methane, and I really haven't done much with it. I do think that method probably works for the Denver metro area, and it might not work in many other places. It seemed to have worked in the Uinta Basin, but I tried it for the Permian Basin and the San Juan Basin, and it didn't. Nothing made sense.
Because it's very, very shallow bottom. But the Tropomi methane is, because it's looking at reflected solar, it's a true column, right?
Yeah, and the other reason I didn't look at it in this application is it doesn't go back far enough.
Right.
But you know, there's enough data now. Right? You could at least look back several years.
I have a question.
Yeah, right.
So a question for anyone on the panel, but other than me, is that one of the exciting things with Tempo is that they will have this lower tropospheric ozone product. And I'm curious sort of how you see that being most useful in a regulatory context.
Well, certainly for Connecticut, I know that, I mean, assuming it's reliable, I mean, it hasn't been proven yet, but if it's reliable, we expect to see the NO2 emissions evolve during the day, the ozone production evolve with them, and that'll be pretty solid evidence where it's coming from. We don't, the modeling all shows that usually for our non-attainment monitors, Connecticut contributes maybe 5 ppbs to non-attainment. New York State, 20. You know, PA, other states. So that's what we're up against, and Tempo is going to really help out with this.
I think it'll really help with forecasting, and forecasting helps with SIPs because you can do the I forgot the term, but anyway, you can characterize what normally happens and evaluate the modeling and things like that. When I was forecasting for Front Range, I used to see a spike in ozone at Greeley first around noon, and then as the upslope winds headed towards Fort Collins, those monitors would spike in sequence. And if you were looking at NO2 at the same time, you could get an idea of what that cold emissions from the Denver metro area and oil and gas field pool in the lower part of the Flat Valley. And the inversion breaks there later than anywhere else. So you've got this big concentrated mass of precursors. And as the mixing height deepens and photochemistry happens, you could, I think, with Tempo see in detail what's going on with that.
Lizzie, do we have any questions or not? Okay, if not, we're going to take one last question from the room.
I'm interested in the ozone production sensitivity that was discussed in terms of formaldehyde now too, and looking at these satellite measurements, it's occurring at 1:30 in the afternoon, about, and that's just one point, right? And for ozone, we're looking at an 8-hour period, and there's been discussion before about the most important time for emissions could be in the morning, if it's going to determine what's going to happen in the afternoon. So in any of your work, have you looked at different time periods from other types of measurements? And I also think that Tempo is certainly could help us in that regard.
Do you want me to take that one? So yeah, I think that's kind of where we're trying to head with the New York field campaign data, and there are certainly other people that have looked at this kind of time of day evolution, but right, as I'm sure you're aware, right, you'd expect that afternoon is going to be probably when you're most NOx sensitive. And so you have this diurnal cycle that you expect in your sensitivity of your ozone production to VOC versus NOx. And presumably there's kind of what we know happens seasonally happening on a daily basis with that solar cycle. And so I do think that having the Tempo data with the NO2 and the formaldehyde, with our ground-based monitoring networks and whatever information content that lower tropospheric partial ozone column has, I think we're going to learn a lot. But I guess my feeling is that the Trogomi analysis is probably going to be more tending towards NOx limited, maybe than is truly the case in these urban core and sort of transitional areas. And so I think that's a really important question that we do need to think about. And I'll just say that the comparison with Laura Judd's airborne data and Scott James's formaldehyde data, so Laura had the NO2, that actually also suggests that Trogomi, even at like the same time of day, was tending a little more NOx limited, which again, when you think about the coarser spatial footprint, is probably what you'd expect. So yeah, I think there's a lot more work to be done.
For sure, yeah. Thank you all for the great talk.